We have a discussion section, so like yesterday, we'll have all the people that gave a talk in this session come up, and you guys can start thinking about questions you want to ask.
So many of the talks before on Gaia searches selected stars which were like removed stars that were hot stars for good reason, but like is that going to change with DR4? Is it like just going to be too hard to search for neutron stars or black holes around OB type stars?
Okay, I can start. Yeah, we had lots of discussions about this also during the workshop in the past week. I think the problem in DR3 is that most of the massive stars got removed from all of the binary catalogs because they tend to be rare and far away with uncertain parallaxes, and the parallax cuts remove them. I think this will get much better in DR4, and Sutkin Janssens made some predictions of what you can expect from astrometry for massive stars. But also in DR4, you'll get epoch RVs for the bright ones, and I think that will be very helpful in the search for dark companions.
Thanks.
Also, DR3 didn't publish velocities for hot stars fundamentally, right? I think that's what close companions was a fundamental indication of DR3 that should be fixed in DR4.
Yeah, so a lot of companions are ruled out. I have a question to you, Kumal. You seem to have found candidates. I didn't quite understand, what is needed to make these candidates black holes. So did you exclude luminous companions of various types for these?
So these are very preliminary. So what I did for the candidates is it's easy to exclude a main sequence companion. That is the first thing we try. What we try later is, can we exclude a stripped star companion? Can we exclude a binary and so on? So those tests are still have to do. But a lot of these systems are highly eccentric. Some of them are hundreds of days and so on. So the idea is also to try to come in from an evolutionary standpoint, whether such a configuration is possible. And it would also be useful to get, for example, UV spectra where a stripped star would show up there, but not in the optical spectrum. So for VFTS 243, for example, I think they really had a lot of diagnostics to really nail down it as a black hole. Right now, we don't have that for these 15 stars, but once we have these select few candidates, we can go deeper for them.
So the stripped star masses would not be in the range where you would expect them to show up as Wolf-Rayet stars or so?
No. The minimum masses are a bit too low. Yeah.
Thanks.
Hi, this is Natasha Abrams from Berkeley. Awesome session. A lot of you guys mentioned spectral disentangling, and I Reese mentioned that it was an assumption that the spectra is time invariant. I guess how does that assumption affect, how good is that assumption? And if it turns out that the spectra is not time invariant, is it possible to get things that are SP1s that are actually SP2s and vice versa?
I think maybe I should take the one. Yeah. That assumption is okay most of the time. Where I didn't show this because it's ugly, but where it really breaks down is if you have emission, because emission is variable. So for a lot of these, or especially the mass transferring system that I had, or where we think mass transfer is still ongoing, if you disentangle around the H alpha line, it basically looks like garbage, just because of that variability. So there's a couple of things that you can do to try and avoid that. Obviously, if you know that you're looking at the Balmer lines, where you're going to be having potential variability, that you just don't disentangle around there, you disentangle somewhere else. There's also some things that you can do where if you think you have an idea of what your spectrum looks like, you can introduce regularization that sort of poses some or places some assumptions about your like underlying spectrum and then tries to sort of push it towards there. That can account for a little bit of this stuff, but really if your variability is extremely significant and you don't have a lot of epochs, then it becomes really tricky with spectral disentangling.
So then I guess, is it more just that it like isn't possible to disentangle the spectrum, or can you get like a wrong result?
You can still disentangle, and the star that isn't variable should still be reasonably well recovered-ish, but your secondary, depending on how the variability actually looks, you have to sort of average over the difference. So if the emission increases and decreases over time, then you basically just get like an averaged version of it.
Thanks.
So the Gaia low metallicity samples are really interesting. Do you have a corresponding not low metallicity sample with enough spectral follow-up to say there's something different in those high RV variables at different metallicities yet?
So I would say all of the orbital solutions have more or less been followed up, and we have an understanding there. I mean, there's only 2 Gaia black holes in DR3, but outside of that, I think different samples have different selection cuts, and they have to be characterized based on their own selection cuts. You basically need to have some proxy for thinking that sample is promising for looking for black holes. So the low metallicity thing is because Gaia black hole 3 is low metallicity, you think it's a place to search for black holes. Otherwise, you might need to say like, okay, if I just look at high Roux, there might be too many contaminants, so I need to do Roux and combine it with something else. So I've not compared just like the low metallicity sample and then everything else, but I don't think there's like a comparably large sample just looking at everything else. But maybe if anybody else has other.
So I'm not sure this is leading off a little bit, but I'm wondering about the low metallicity of the giants which you found for one of the black hole binaries. I'm wondering whether there is any connection to be done with the searches for extremely low metallicity stars, from the point of view of nucleosynthesis. There is surveys, I don't know them, but there have been surveys going on to hunt for such stars. Many of them may be single epoch, but I think there's also an interest to find binary companions there, because many of the carbon-enhanced metal poor stars seem to have white dwarf companions and so on. So is there any overlap in the two strategies, so to speak, in hunting for low mass halo stars to find companions?
Yeah, I'm not sure about any overlap there, but.
I mean, I think the most interesting thing at low metallicity, and sorry for taking over the mic, is that you have a very thin convective envelope if you're on the main sequence. So you can accrete a tiny bit, and it'll basically stay on the surface. That's not the case in Gaia BH3 because it's gone up the giant, so now it has a thick branch, so it has a thick convective envelope. But for that one, you can show if you had the same star a billion years ago when it was on the main sequence, even at 10 AU, if it accretes, 1/1,000,000th of the supernova ejecta of the companion, if it had a supernova, you have a chance of detecting something. So I think maybe that's if you find a companion at low metallicity that still has a thin convective envelope, you have a much better chance of checking did it form from a primordial binary where there was some accretion from a supergiant companion, or from either a supernova or from a wind from a companion.
Hi, thank you so much for the talks. They were all amazing. And I want to ask you, how do you see, the future with Roman? With astrometry with Roman, yeah.
Who wants it?
Thank you, Hannes.
Yeah, no, I think we have other Roman experts here, but I would say the getting light curves for these objects is helpful, especially for the shorter period regime, where you expect ellipsoidal variation, and then also the searches for microlensing black holes. So I think that's where it's most helpful. Can people, do you want to add something to that? I think for the longer, yeah.
So I think Roman astrometry will also be very good in the galactic plane and galactic bulge, where Gaia is not so great today because of crowding. And the precision is plenty good enough for what you want to do for the nearby samples. So I think there's a lot in there, especially for main sequence black hole combos.
I also have an unsolicited comment on Roman. I mean, I think, remember, Gaia has been dead for a while. I mean, the releases are going on, but I think having, in many circumstances, a much later epoch, single point, can tell us interesting things, given that all things are tertiaries, right? Whether you actually have accelerations that reflect something very long, long periods. So I think there it might help.
All right, lunchtime.